Welcome, my name is Dr. Richárd Wéber. I am from the Faculty of Mechanical Engineering and Department of Hydrodynamic System. And today I will speak about the hydraulic and biological modeling of water distribution network. As you may know, the water distribution networks are one of the key infrastructure elements of every modern settlement, providing clean, safe drinking water to the inhabitants and the industrial consumers. For a model, we need a hydraulic model first. We are using GIS data, Geographic Information System, to build a topology. We add the pumps and tanks and active valves to the model. We do some corrections to the database. And finally, we add the demands to the model. And if we are lucky enough, we will get something like this, that is a model for a real-life water distribution network. To solve the equation, we need the hydraulic solver. We have an in-house solver that is called Staczi. It is developed by the department. It solves the edge equations and the equation for the nodes. And as an output, we can get the pressure and the volumetric flow rate. This software is freely available. It is open source on GitHub. Let me speak about the vulnerability. What happens if we have a pipe burst? For example, here we have a little toy network, and we have a pipe failure. Then the corresponding utility company must shut down this segment, this island, by closing valve B, D, and E. And the question is, which segment is more important than the other segments? We need two metrics. First is the relative failure rate that tells us what is the probability of having a random pipe failure at the segment. We can use pipe material data, pipe length data, etc. And the other metric that we need is the relative consumption outage, which is why we need the hydraulic model. It is also a number between 0 and 1, and it tells us, in case of a random pipe burst, how much water is not served during the reconstruction. And we have two metrics. The local vulnerability is, by definition, is the product of the two. So this means that the segment is vulnerable if there is a lot of pipelines and, in case of an isolation, there is a large outage. And this way we can, for example, plot or colorize the network by this metric, and we can identify the segments, the areas which are more important and where the corresponding utility company must be aware of any pipe burst. This is another example. Let me speak about the water quality modeling. The quality of water is very complicated. It depends on residence time, chlorine concentration, temperature, pipe material, the initial quality of the water, and then many others. Our approach is to build a model that can predict a qualitative distribution in a water distribution network. The question is, which areas might be sensitive in terms of water quality. For this, there are mathematical models already developed in the literature that describes the biofilm growth and detachment and the substrate transport and diffusion. But the problem is that these mathematical models typically contain several parameters which are really hard to estimate, to predict. That's why we built a laboratory measurement that is a semi-real-life water distribution network. And with this measurement equipment, we would like to adjust the mathematical, we would like to calibrate the mathematical models, and then with the correct parameters, we can introduce these mathematical models to the hydraulic solver, and that can predict the sensitive areas in the water distribution network. Thank you for your attention.